so are Rand and Ed, to talk to you today about something that we're all very passionate about, which is the nuclear industry. We'll go through why we believe, why we're very passionate about the nuclear industry and why we think it's a very exciting industry to work in. But first we'll introduce ourselves. I'm Lauren Corkum. I'm the NAYGN Durham Vice President. I also went to Queen's for engineering chemistry.
Hi, I'm Rand Kalia. I'm the NAYGN Durham Treasurer, and I went to UofT. I'm OT7 plus PUI for engineering science, and I did the nano stream. So I work over in Pickering right now.
And hi everyone, my name is Edward John. I'm the current president for the Development and Young Generation Nuclear the Durham chapter, and I'm a proud fellow UofT alumni as well. I graduated in 2005, OT4 plus PUI in electrical engineering.
Great. So the NAYGN Durham chapter, which is what we're representing today, is an association of young nuclear professionals and students 35 years or younger, or with 10 or less years of experience. So our focus is professional development, networking, community outreach, similar to kind of IEEE, but for the nuclear industry. So moving on, why we support nuclear power. So I've had the pleasure to present at a couple of public hearings about the nuclear industry. Nuclear power is a low-cost, reliable, and environmentally friendly energy source. So we're talking about an energy source which is comparable. Ram will go through this a little bit later in the presentation, but comparable to wind in terms of carbon dioxide per kilowatt hour, and it offers a solution, a low carbon solution, which is competitive with other with petroleum-based energy sources. Yeah. So the nuclear industry supports 71,000 jobs in Canada, and the Darlington refurbishment will extend the benefits of nuclear power further into the future. So the outline for today. So today we're going to talk about the past, present, and future. Before I started working in the nuclear power industry, I had no idea that Canada has played such a large role in the development of nuclear reactors here in Canada, as well as all over the world. We've had a very long history in this type of field, and so that's what we'll be discussing, as well as the design of CANDU reactors, how they work, what's the kind of the design philosophy, and the future. What's on the horizon for the nuclear industry? What will we see in 20 years, 50 years? What are people looking forward into the future? All right, so I'll pass it on to.
Just before we move on, I just want to add one point. The NAYGN organization that we came here to represent today is a continent-wide organization. We have chapters in Canada, in the US, and in Mexico as well.
Mm-hmm. Okay, so and I'll hand it along to Rand to take us to the past of nuclear power.
Okay, thank you, Lauren. Hi, everyone. So I'm going to be talking to you about the evolution of nuclear from its first inception into where we are today, and then I'll pass it on to Edward to talk about our current status. So, nuclear power. When we think of nuclear power, the first thing that comes to mind is, weapons of like the nuclear weapons and things like that. But nuclear energy is a very big part of nuclear power. So nuclear power consists basically of using nuclear processes to generate electricity. That's the simplest way to put that. Now there's three types of nuclear power that you can get. So I've described it briefly over here. The three main types are fission, so nuclear fission, nuclear decay or radioactive decay, and nuclear fusion. Just a little bit about them in brief. So fission is the one that's most widely used. It was discovered in the early 1930s. And it basically accounts for about 13% of the world's electricity generation. So most of the reactors that you see in the world are all nuclear fission reactors. Nuclear radioactive decay is basically a process whereby we all know about radioactive elements that exist. Certain isotopes of elements are radioactive and they decay. They have a certain half-life. So as they decay, they also emit certain amounts of energy. And while this energy is very minute sometimes, in most cases, it's also very useful to be harnessed for long-term energy supplies. So examples of nuclear decay being used are things like the ESA's space shuttle, and actually one of their satellites. It actually used radioactive decay as one of the main power sources because it went on a mission into space, it stayed there for a long term period, and basically it needed the energy to just power basic electronics. Nothing large scale like powering your homes or powering our streetlights and things like that. And then the third method of nuclear power generation is nuclear fusion. Now, nuclear fusion is still theoretical in Earth, so we're still trying to figure out exactly how to perfect it in terms of a net positive reaction for nuclear fusion, but we all know the most famous source of nuclear fusion is our sun. So it always undergoes fusion, converting hydrogen into helium, and it produces mass amounts of energy. So nuclear fusion is actually the future of nuclear power, and it's termed as one of the sort of the barriers to unlimited energy. And Lauren will talk a little bit about that as well. So, how was nuclear power discovered? So basically, I'll go into more about nuclear decay and nuclear fusion and fission and how that was discovered. So fission is the one that's most commonly used, and that was discovered in the early 20th century. So like I mentioned, in 1920s, 30s. It was discovered that radioactive elements have immense amounts of energy stored within them, and they release this energy. And the way they release it is according to the principle of mass energy conservation. So basically, as they decay and they split off into certain elements, some of the original mass is actually converted into energy as well. And that energy is what we can utilize in generating power in nuclear power. So how did this start off? How did we discover about nuclear power? It all started off when two very famous scientists, Fermi and Chadwick, so James Chadwick and Enrico Fermi, discovered the neutron. So Fermi was the one who discovered the existence of the neutron, and they actually discovered that if you bombard certain elements with a neutron, it actually helps in breaking up that element into further elements. So this is where the actual process of nuclear fission was discovered. So I've given a small representation of what fission involves. So basically what it is you basically fire a very charged particle, neutrally charged particle, a neutron, into a target nucleus. So nucleus, like we all know from chemistry, is made up of protons, electrons, and neutrons. So when the neutron strikes the nucleus, it undergoes a process called nuclear fission. And basically the nucleus, the element, splits off. And it splits off into certain products, byproducts, called fission products, but also into energy, as well as other neutrons. So this is how this whole process of nuclear power came into play. So one neutron striking a radioactive element could actually cause fission products, energy which we can use, and also further neutrons, so you can maintain that chain reaction. Because just firing one neutron and having energy won't really help us, because then we'd have to have a constant particle generator firing at that. So that would actually eat up most of the energy and wouldn't actually be electrically efficient. So just some of the history into the development of nuclear power. After World War II, that's when nuclear power really gained its momentum, and it started being used for electricity generation. So the very first reactor to generate electricity using this process that I mentioned, nuclear fission, where you fire a neutron and you have that chain reaction that can be maintained, where subsequent neutrons strike elements. The very first one was in the US, in Idaho. It was the EBR-1, or Experimental Breeder Reactor. And it was inaugurated on December 20th, 1951. So you can see the history of nuclear power. It's been there since 1951. Okay, anyways, I'll just go off the PowerPoint here. So that was the very first reactor to generate electricity. The next reactor to actually power the grid. So it generated electricity, but then it didn't actually get connected into our grid. The grid is what we all use. You see all the high transmission lines, high voltage transmission lines. So the very first reactor to power the grid was in Russia, or former Russia, the USSR, and it was commissioned on June 27, 1954. And it was called, pardon my pronunciation here, but Obninsk Nuclear Power Plant. And that was the very first instance where it was commercially found that we could actually generate electricity and feed it to the grid to power our homes, etc., things like that, using nuclear power. And then that was a very small scale, just the experimental one. And then the first large-scale commercial industrial reactor was in England, commissioned in England on August 27, 1956, called Calder Hall Nuclear Power Plant. So that was in the 50s. But since the 50s, nuclear power has grown steadily. We've seen a huge increase in nuclear power, and the applications have varied a lot. So you've seen applications in terms of naval vessels, so submarines. There's a lot of submarines that are powered by nuclear reactors, so they actually use that electricity to power the systems on the submarines, and as well as aircraft carriers in recent years. So how did this development occur? Basically, in the 1960s, there was about 1 gigawatt of nuclear power being produced to actually feed into the grid. That grew dramatically into 300 gigawatts by the 1980s. So in the 60s to 80s, that's when the nuclear sort of the renaissance happened. That's when nuclear power is really being developed. In the 70s and 80s, just to give you sort of a picture of the magnitude of that. But 150 gigawatts was in construction. So out of the 300 gigawatts that we ended up in 1980s, about 50% or more of that was in construction in the 1970s and 80s.